All right, so back to oscillators. I wanted to kind of revisit what I was talking about with like the frequency differences between startup oscillation and steady state. They are going to be a little bit different, so I wanted to just kind of briefly mention what that will be. Oh, wrong pen. Wrong digital pen. Okay, so we're going to have two free running frequencies for the oscillator. We're going to call one of them omega naught small and one of them omega naught large. So the way that we get the oscillator to start up, we use the small signal gain conditions to get the oscillator to start. And then once it reaches steady state, it's operating under large signal conditions, meaning the conditions that the signal swing is large enough that it affects the DC operating point and other characteristics of the device. The small signal is dominated by, or the small is dominated by small signal, the large is going to be dominated by large signal. So assume that each oscillator stage in our ring oscillator has a delay equal to T inverse or T inverter. So just some period or some delay from the input to the output of the inverter. And we have three of these inverters. So we can say that the large signal free running frequency is equal to 2 over pi over 6 times T inverter. Because for one cycle of oscillation, you have to go through the inverter chain completely one time and then go through it again. Now, the thing about T inverter is that this is determined by large signal characteristics of the device. It's going to be determined by the capacitance and then also the nonlinear current that comes from the device. It's very difficult to find that mathematically or analytically. So normally what you have to do is just put large signal swings into the inverter and figure out what the delay, the propagation delay is from the input to the output under those large signal conditions. Now, conversely, we calculated the small signal oscillation frequency yesterday, and we said that that was equal to square root of 3 times omega p. And we know that omega p is determined simply by the RC circuit. Okay. So the oscillator is going to start up at omega naught small, and as the poles drift from the complex plane onto the imaginary axis, it will stabilize to omega naught large. Ideally, those will be fairly close to one another, but they don't have to be equal to one another exactly. Okay, so any questions about that? This is true for most oscillators, so not just ring oscillators. The nonlinear dynamics will dictate the large signal oscillation frequency. The small signal will dictate startup. So now there might be different values for the different types of oscillators, but the concept is very similar. Okay, so we're going to look today at a one-port model of oscillation. So in the last one, we injected a signal and kind of looked at feedback. Here, what we're going to say is that we have just a one-port connection between an active circuit and a passive resonant circuit. So if we look back In the direction of the active circuit, we have some impedance ZA, and in the direction of the resonant circuit, we have some impedance ZF. And these are complex impedances, so we can say that ZA is equal to RA plus JXA, and ZF is equal to some RF plus JXF. And for oscillation to occur, we know that we need ultimately the phases to cancel of these signals, or we need the phase of the active circuit to equal the phase of the passive circuit, the magnitude, but opposite phase. Or really what we're saying is that XA plus XF needs to equal 0. And we also know ultimately that the resistances have to be equal to one another, or the sum of the resistances have to be equal to, or I should say equal to or less than 0. This is really the condition that we have for our resonant circuit, right? The resonant circuit, we have some X from a capacitor, some X from an inductor. Those two have opposite signs, so they cancel one another out. And ideally, if we want the LC tank to oscillate perfectly, we need the resistance in the tank to go to 0. Now here we're adding the condition that RA plus RF needs to be less than or equal to 0, because ultimately we're probably going to need to make it slightly negative in order to start an oscillation. But once the system is oscillating, it will settle to a value of 0. Okay, so what we're really looking at ultimately from this definition is that the active circuit is going to provide a negative resistance. And the frequency of oscillation, omega naught, is going to be defined by a resonance of the tank coupled to any parasitic reactance in the active circuit. Now, is there any such thing as a negative resistance? A real physical negative resistance? Well, we can make something that looks like a small signal negative resistance, but that's not a real negative resistance. What we're really doing is we're pumping energy into that circuit, and we're extracting a little bit of it in order to cancel out the energy that we lose in the tank. So here's our negative resistance generator. Salican is right. It is a cross-coupled transistor. There are other ways to generate negative resistance. We'll look at one a little bit later today, another one later today as well. So here we have cross-coupled NMOS devices. The gate of one NMOS is coupled to the drain of the opposite NMOS. So here we have M1 and M2. We can make a simple model for this circuit. We have a voltage dependent current source that's equal to GM times V1. One that is equal to GM times V2. And the voltages that are developed across these are due to the opposite gate. So this will be V2, and this will be V1. That's this cross-coupled connection between the drain of one side and the gate of the other side. Now, if we put a test voltage source across the circuit with a voltage of Vx, and we measure the current Ix that flows through the test voltage source, we can write a KCL expression. So we can say that Ix is equal to Gm times V1, or equal to minus Gm times V2. We can also say oops, 2Ix is equal to Gm times the difference between V1 and V2, which is equal to the value of Vx, so 2Ix. Ix is equal to minus Gm times Vx. In other words, Vx over Ix is equal to minus 2 over Gm. So there's our negative resistance. Vx over Ix is equal to minus 2 over Gm. All right, if we want a big negative resistance, what do we need to do to the transistor?
Very small transconductance.
Yeah, small transconductance. And we can achieve that in a couple of different ways. We can make the overdrive voltage big. We can make the current small. We can make W over L small, all the different ways that we might change the GM of the device. So we'll get back to the oscillator in a second, but we have a simple way to make a negative resistance cross-coupled transistors. Now let's look at our parallel resonant tank. So here's our parallel RLC tank. Now we know that the resonant frequency of this tank is equal to 1 over the square root of LC. And we know that likely this tank also has some resistance. And we're not going to necessarily add a physical resistor here. The tank has a finite quality factor because the components are lossy. So we're just going to have some R that's associated with the loss in the tank. And that is going to be measured by the quality factor of the tank, which is equal to either R over omega naught times L, or is equal to R times omega naught times C. Actually, I shouldn't add the omega naught. This is just any frequency. Of course, we're going to be using it right around omega naught, most likely. Okay, so it's lossless. If we have the white circuit, when we add the resistor, it becomes a lossy circuit. Now you can physically add a resistor if you want to, but I can't think of any practical reason why you'd ever want to. It's going to cost you power in order to counteract that resistance. All right, so just note R is, I'm just going to say never added. Comes from the loss primarily in the inductor. Capacitors do have loss, but their quality factors are typically significantly higher, so we're just going to say loss in the inductor. Remember when we talked about passive circuits, the loss in the inductor is due to eddy currents in the substrate. Metallization, or ohmic losses. And those might get worse or better depending upon, although they might get worse depending upon skin effects of current flowing through the metal. So remember, at high frequency, the fields that are internal to the metal push the current carriers to the edge of the conductor, and that causes the cross-sectional area that current is flowing through to be reduced, or increases the resistivity at higher frequency. Okay, so we know that the negative resistance in the tank must ultimately be enough to overcome the resistance, the negative resistance in the cross-coupled pair must be enough to overcome the losses in the tank. In other words, we have a condition that says that -2/GM must be greater than or equal to the magnitude of -2/GM must be greater than or equal to the tank resistance. Let's label this R tank just so we can see what we're talking about. All right, so now let's make a simple oscillator. So the simplest oscillator looks something like this. We have a cross-coupled pair. We have inductors going to the supply voltage, and we have capacitors that are being, I've drawn them as varactors. So whenever you see this symbol of a capacitor with an arrow through it, this is called a varactor, which is a voltage variable capacitor. How do we make a varactor? MOSFET, yeah. Anything else we might use?
It's traditionally diode. I'm not sure.
Yeah, any PN junction really works. So a MOSFET, we're actually not necessarily just using the full depletion region of the PN junction. But if we have a PN junction and we have a depletion region, we know that we can modulate the thickness of the depletion region, which is effectively changing the thickness of a parallel plate cap. And that makes the voltage variable capacitor. Now we can also add some additional tuning mechanisms, so we can make this a switched cap circuit if we want to. Right now I'm just drawing it assuming that all of our capacitance is going to come from some varactor. Now if we were drawing this in the PDK that we have, we would probably use something like a symmetric inductor with a center tap. Where the total inductance was equal to L. Half of it would go to one side of the circuit, half would go to the other side of the circuit. All right, so it's important to note basically that the inductor, the reason that we have L/2 and 2C is that the passive components are in series with one another relative to the virtual ground that's in the center. And so that's why I've doubled the value of the capacitor. 2C in series with 2C is equal to C. And have the value of the inductor L/2 plus L/2 is equal to L. All right, now our negative resistance comes from the GM of the circuit ultimately. Remember, GM is equal to mu times Cox times W/L times VGS minus VTH. This quantity, remember, we call VOV. It's also equal to 2 times ID over VOV, and it's equal to square root of ID times mu times Cox times W/L. Now, what we're ultimately doing here is we're keeping the current flowing through the drain, the DC current flowing through the drain constant by just biasing it with this current source. So this form 2ID over VOV is the one that we'll look at. So you can imagine that if you assume a quality factor of 10, a bias current of 1 milliamp, an inductance of 1 nanohenry, you can calculate some VOV and some capacitance to provide an oscillation at 1 gigahertz. You can go through and do that exercise a little bit later. I'll fill in what the values need to be, but it's pretty trivial algebra or arithmetic really, to go through and calculate how to make an oscillator. Now, cross-coupled oscillators are really liked because they're very simple to make, and they're almost guaranteed to work as long as you bias the thing correctly. And like I said, we can add switch capacitor banks into these things, so we can add calibration to guarantee that we have the range covered of our oscillation. So these are nearly ubiquitous in CMOS circuits, but cross-coupled oscillators don't give us the best phase noise performance, and so there are other oscillator topologies that do. Now, I say that with a caveat. In recent years, people have taken to making these Class C and inverse Class F oscillators where they're doing pulse shaping with the network. They're trying to shape the harmonics and get the drain current voltages to not overlap. And when they do that, they can create conditions that cause the phase noise to be better in the oscillator just by doing that pulse shaping. And they do that with cross-coupled oscillators. But we're not going to talk about that now. We'll talk about another type of oscillator that's commonly used if we want better phase noise performance, and that is a Colpitts oscillator. I'm going to skip this and come back in a moment to the analysis. This is the simple concept for a Colpitts oscillator. We have a capacitor divider. We add some inductance. And because we add the inductor, and it probably has a lossy, it's probably a lossy inductor, it's going to bring in some parasitic resistance. So we have our inductor, the value of L, parasitic. Now, let's go back. There are a number of different ways to make a Colpitts oscillator. We'll look at a few different forms in a moment. Let's go back and look at the analysis. So first, we know that we are going to put the inductor across these two terminals of the Colpitts oscillator. So let's put a voltage source into the circuit with a value of Vx, and we'll measure the value of current Ix that flows through the circuit. So let's replace the transistor with a small signal model. Okay, so here's our small signal model. This has I'm going to say that the value of the voltage here is V2. The value of the voltage here is V1, and the small signal model says that GM times the current is equal to GM times V1 minus V2. That's really the gate to source voltage difference. And then we know that the value above the gate, above the test voltage source, is equal to V1 plus whatever value Vx is. All right, so we can write a KCL expression. I should say a KVL expression, sorry. V1 is equal to V2 minus IX over S times C1. Or we can say that V1 minus V2 is equal to IX over S times C1. And then we can go to the drain node and we can say that IX is equal to GM times V1 minus V2 plus V1 plus Vx minus V2 over the impedance of the capacitor SC2. Oh, sorry, over 1 over SC2, which means times SC2. And then we can take these equations, make some substitutions, and ultimately show that Vx over Ix is equal to 1 over SC2 plus 1 over SC1 plus GM over S squared times C1 times C2. And if we substitute S for J omega, we know that this is minus GM over omega squared C1 C2 plus 1 over S times C1 plus C2. So we have an equivalent circuit now where we have a negative resistance. The real portion here is negative. And we have a reactance that's equal to the series combination of the two capacitors. So this is our negative R. This is the reactance of the active circuit. Now let's go back. We know that we're taking that equivalent circuit and we're going to put it across the inductor that we're adding. That inductor is bringing a real loss with it associated with the RP value. We know that if we want to get this to oscillate, our oscillation frequency is going to take the form of omega naught is equal to 1 over square root of L times C total. C total is equal to C1 in series with C2. I know I just used the parallel sign, but
Yeah, I take over.
No, I think I put my hand in a way.
Oh yeah, happens.
That's fine.
It's like Windows narrators, like narrator on.
Well, you know, the pin mechanism is supposed to turn off the screen so that it doesn't, but that seems to, I mean, every once in a while that goes out the window. C total is C1 in series with C2. When I'm adding capacitors, I use the parallel sign just to make sure we know that we're adding them as capacitors in series. But that's just my crazy notation. Those two capacitors are in series, so they're adding as 1 over Z. All right, here is our, for our oscillator to start up. You know that negative resistance portion minus GM over omega squared C1 C2 has to be greater than or equal to RP to overcome the tank resistance. Now there are different forms of Colpitts oscillator, so this is just the concept. I've shown you a concept where we put two capacitors in series around the transistor. We can put those in series around the transistor and across different terminals. We have a common gate, common source, and common drain form. So here's our common gate form. Now, I'm not drawing the DC biasing here. We'd have to do something to cause current to flow through this. We'd probably just put a current source here and bias the gate with a DC level, but anyhow. What's important is that the two capacitors are in series with one another and they're in parallel across the inductor. And you can see that because the capacitor is tied to one terminal, or one of the capacitors is tied to one terminal of the inductor, and it goes to the top terminal goes to the supply, which is a virtual ground. The bottom terminal, C1, goes to a ground, which is also a virtual ground. And so those capacitors are in series and they're in parallel with the inductor. We have a common source form. That's actually more or less the one that we just showed you. And we have a common drain form. Okay, all of these will oscillate. Remember, it's possible. So even though only the common source stage can give us both current gain and voltage gain at the same time, they can all give us power gain, and so they can all provide enough. They can provide a signal to oscillate. Can I do this with a PMOS? Of course, PMOS will give me a GM. What are some reasons I might choose a PMOS over an NMOS? Lower flicker noise, so I'm going to get better phase noise performance. Yeah. Why would I not choose a PMOS? Lower mobility, which means I probably won't be able to operate to as high a frequency. Yeah. So NMOS will probably give me a higher frequency, but worse phase noise. PMOS is going to get me lower frequency but better phase noise performance. And I should mention, we can do these with bipolar transistors as well. Bipolar transistors give us much better phase noise performance because bipolar transistors have much lower flicker noise corners than CMOS devices do. Different mechanism creates it. We can also show what those things look like with biasing. Here I've just drawn some of the examples of the circuits where we might add biasing. So the common gate, common source, and common drain, all with some DC current source that's pushing a constant current through the device, and then maybe some DC voltage level to bias them so that they stay on. All right, well, you might imagine that if we can do the series combination of capacitors, we can probably do the series combination of inductors. And indeed, there's one called the Hartley oscillator. So here, I'm going to put a capacitor across the negative resistance. You can guess that that series combination of inductors around the transistor will ultimately end up creating a negative resistance, and then that negative resistance that will have some inductance as well, and then we'll put that in parallel with the capacitance. Indeed, if we look into the terminal here, looking at what the input impedance is, we find that Zn is equal to minus omega squared times Gm times L1 times L2. Oops, let me move this a little bit. And my reactance is J omega times L1 plus L2. So I have this negative R, and I have L1 in series with L2. Okay. Now, where is my loss coming from? I'm going to have some RP1 associated with the one inductor, some RP2 associated with the other inductor. So, so my loss is still primarily going to come from the inductive components. RP total is equal to RP1 plus RP2. That needs to be less than the magnitude of the negative resistance and of course the oscillation frequency is 1 over 2 pi square root of C times L1 plus L2. Yeah.
Wouldn't parasitic capacitance of the device also like this?
Yeah, there'll be some parasitic capacitance that'll add in parallel with, or more or less with the, so what we'd have to do is in the analysis go and add CGS and CGD, do the small signal equivalent circuit, calculate that, and find out what contribution it would make to the overall tank. But yeah, you're right, there'd be some parasitics. Anybody know what Hartley is famous for? Really famous for, other than this oscillator, which is a fine oscillator? Something else that we use in RF circuits. Anybody remember the Shannon-Hartley theorem? I know, people remember Shannon, they don't remember Hartley. It's a shame. Hartley was actually a graduate of University of Utah, where I was a professor, so that's why I remember Hartley. Anyhow, Hartley actually, Shannon, I think, did more of the information theory work on it. Hartley actually played a big role in proving the theory. So experimentalists get credit also occasionally.
Well, you can't prove something with an experiment.
Well, I guess you can fail to prove the negative.
Disprove something.
Yes.
I don't think you get a lot of credit for that, though.
No.
Secret design. We failed to prove the product works.
Okay. Couple of points about these. Generally, the Colpitts is preferred to the Hartley. Why do we prefer the Colpitts?
One inductor.
One inductor, that's right. What's going on? Now, I will say that if we were concerned about the size alone, we could use for the Hartley but the transformer is still probably more lossy. So we're going to prefer the Colpitts. I'm not going, I might come back to the amplitude and startup conditions in a little bit. I'll post the derivations here for how we determine startup conditions. I'll just say that generally we need to make the negative resistance slightly bigger than the positive resistance in the circuit in order to get the circuit to start up. For the cross-coupled, we typically make negative resistance about 2 to 3 times RP to get the circuit to start up. There's a reason that we don't see as many Culpits and or Hartley oscillators, and that's just that they're a little bit trickier to get to start up, and they typically have a little bit narrower tuning range than the cross-coupled oscillators. So you see a lot of cross-coupled oscillators or people really trying to get the cross-coupled oscillator to be satisfactory. And that's why you've seen a lot of the work on trying to reduce the phase noise contribution of cross-coupled oscillators because they do just ultimately want to oscillate if you provide any reasonable condition. All right, so I'll fill in some of the large signal operation of the device a bit later. If you're interested in following along, you can do that. But for the rest of the time, I wanted to talk about something that's very important for communication circuits and oscillators are at the heart of it, and that is phase noise. So we kind of just brushed by it the other day, and I think it's kind of important to understand some principles associated with phase noise and oscillators. All right, so what is phase noise? So the principle that I showed you the other day is that we have say some sine wave, and let's just say that that sine wave is centered around DC. Now, ideally, that sine wave every period of the sine wave is identical to every other period of the sine wave. In other words, I could just chop the sine wave into one period chunks, line them up on top of one another, and I would see a perfect sine wave. What do I see in reality if I do something like that? I'm going to see a cloud of uncertainty. So there will be like a cloud of uncertainty associated with the sine wave. Now, the mean or the center of that cloud will be where the sine wave should be. But in reality, every point on the sine wave might be deviating from where it should be, and that's just due to random fluctuations that occur in the circuit due to noise. Active circuits have noise, passive circuits have noise, so I never know exactly where the signal is going to actually appear, but I have a statistical idea of where it's going to appear. All right, so let's consider a signal x of t equal to A times cosine of omega naught t plus some term phi sub n of t. And this term is our phase noise. All right, now we're going to consider that hopefully the deviation, that phi sub n of t, is small. In fact, we're going to say that it's much, much, much less than 1 radian. So very tiny. And if we do that, we can make the following approximation for x of t. X of t is equal to A cosine of omega naught of t minus A times phi sub n of t times sine of omega naught times t. Just using one of our trigonometric identities. Now, what this ends up looking like is we have this portion that is equal to a naught times cosine of t. So we have some center frequency that's centered on omega naught of t. And then we have a portion that is going to look like the phase noise skirts that I talked about the other day. Okay, and we can actually calculate those exactly nowadays. I'll provide links to a couple of papers that do the analytical work to this, but you know, it is more or less shaped like a signal that decreases in amplitude as we get further away from the center frequency. All right, so let's go back to quality factor. So we're going to go back to the quality factor of an LC oscillator, and let's remember our first definition for quality factor, which is omega naught times the energy stored in an LC tank divided by the average power dissipated in that same tank. So here's our LC tank. When do we get the maximum, where's the energy stored when the voltage is maximum across the tank?
Capacitor.
On the capacitor, yeah, exactly. Now, when that happens, when we have the maximum voltage across the capacitor, that's when we actually have the maximum current flowing through the resistor, V over R. Okay, so we can say that E max is equal to I peak times R, and also that the energy in the capacitor is equal to 1/2 times C times the voltage squared. The voltage is I peak times R squared. So there's our energy in the capacitor. Now at resonance, Z of LC goes to infinity. So at that point, we can figure that the average power, P average, is equal to 1/2 I peak squared times R. So voltages and currents are in phase. We deliver power to the resistor. That's the power that we're going to deliver. So going back to our definition for Q from a moment ago, Q is equal to omega naught times EC over P average. And this is equal to 1 over root LC times 1/2 C times I peak times R squared over 1/2 times I peak, oops, squared times R, or ultimately, if we make we invert the equation, we can show Q is equal to R over square root of L over C. Okay. Now, this what does this denominator term look like? You've seen it before. Square root of L over C. What does that look like?
Characteristic impedance.
Yeah, characteristic impedance. Yeah. This is the characteristic impedance of the network. Okay. Now, we can substitute, if we want, that omega naught is equal to 1 over root LC. And if we do, we'll come to those more familiar forms of R over omega naught times L, or R times omega naught times C that we've seen before. There are a couple of alternative definitions of Q we're going to look at. So one is one that we've used already, the sharpness of the frequency response, of the amplitude response in particular. So if we've looked at a tank, a purely resonant tank before, we know that it might have a shape like this. It has a center frequency omega naught, and it has some bandwidth where we're at the minus 3 dB points, and we say that Q is equal to omega naught divided by the F3 dB bandwidth of the circuit. Now, if we calculate Q in this way, what you'll find, or what you should find, is that they are exactly equal to one another. Now, where this gets a little bit tricky is when we don't have exactly parallel resonant circuits or exactly series resonant circuits. Then we might have some other things influencing the shape. But if we have purely parallel resonant circuits, these definitions are all the same. And we have another definition of quality factor that we can use. Sometimes it's easier to find one of these than the other, so that's why it's handy to know more than one of them. So if we have the parallel resonant circuit, we can also measure the phase response of the circuit. Now we know for this particular circuit that the phase should be positive at low frequencies and negative at high frequencies. The voltage should be leading the current at low frequencies and lagging the current at high frequencies. Exactly at omega naught, we know that the reactances should be completely canceled with one another. In other words, the voltage and current should be in phase with one another. So there should be no difference. So we know that we go to 0 at the resonant frequency. So an alternative definition for Q is that we're going to relate this to the slope of the phase response. We're going to say that Q is equal to omega naught over 2 times d phi by d omega. So for oscillation, we're operating around that center frequency omega naught. And we know that the phase goes to 0 when omega naught, sorry, when omega is equal to omega naught. If the frequency deviates from omega naught, Q is basically relating to how hard the VCO has to work to restore the phase back to that zero crossing point. All right, now, obviously, the steeper the slope, the easier it is to force the signal back to omega naught. Less work has to be done by the active circuit. So we anticipate that means a higher quality factor. Now, importantly, all right. It's important to know a few of these, like I said, because maybe sometimes it's hard to find one versus another. Sometimes it's easier to get one of these, also, especially in measurements. It's sometimes easier to get a measurement of one of these versus another. All right, so let's look at how this all relates to phase noise. So let's go back to our two-port model of an oscillator. And we're going to use two-port model because we want a place to inject noise into the circuit from an external mechanism like a control voltage, but also maybe internal mechanisms like device noise, thermal noise from parasitic resistance, and so on. So here we have so we have noise from our internal elements, and then we're going to add noise externally. Now I'm going to show this coming from, say, a control voltage if we were making this a VCO, but it could also come from the power supply, for instance. Okay, so first we're going to look internally to the VCO. So let's go back to our transfer function. So y of s over x, we labeled this y and this x before, is equal to h of s over 1 minus h of s times f of s. That's our first order control loop. And we can ultimately say that h of j omega is approximately equal to h of j omega naught, so something right around the resonant frequency, plus some delta omega times dh by d omega. really here we're looking at saying this is where omega is deviating away from the resonant frequency by plus or minus some delta omega. All right, now for oscillation, we know that the h of j omega naught needs to equal 1. And if we made our circuit well, typically delta omega times dh by d omega is small, much less than 1. And if we go back and make a substitution into our transfer function, we can say then that y over x of s is, y over x of omega naught plus delta omega is approximately equal to minus 1 over delta omega times dh by d omega times f of s. Okay, so our noise component is multiplied by this transfer function when it shows up at the output. This is like a gain term for the noise. All right, now for noise, we work in power spectral density. Remember, noise can be always has a zero mean value, so we tend to work in power when we talk about noise. So our transfer function y over x squared is equal to 1 over delta omega squared times dh by d omega squared times f of j omega squared. All right. Now we're going to look at this dh by d omega squared term. We're going to use the polar form. So h of omega is equal to the magnitude of h times e to the j phi. dh by d omega is equal to dh by d omega plus j times the magnitude of h times d phi by d omega times e to the j phi. And if we square this all, 2 minutes at dh by d omega, I'm under pressure. All right. We'll write the algebra quickly and then get to the punchline, hopefully. Okay, so our transfer function is equal to 1 for oscillation. We said that this was a small value earlier. Small value squared is smaller. And we can rewrite 4 as y over x j omega squared is equal to 1 over delta omega squared times d phi by d omega squared All right, there's our Q definition that we saw a bit ago. After doing this, we can reduce this to Q. And ultimately, we get to an expression that says that the transfer function is equal to 1 over 4Q squared times omega naught over delta omega quantity squared. Now, this is a famous equation, and it's called Leison's equation. Leison was a professor at Stanford, I believe, and there's a Proceedings of IEEE paper from February of 1966. And interestingly, he's studying oscillator phenomena and looking for what causes phase noise, and so he's doing it mostly by doing empirical observations and trying to fit curves to things, and maybe also doing some theoretical derivations like so. Now, he predicts a 1 over f squared dependence on phase noise as the frequency deviates from omega naught. Okay, now is that what we really see? No. Okay, in real life, the noise gets down to some point, and then we can't get it below the thermal noise floor. It's thermal noise, and that's it. Now, beyond this, of course, if you get really close to the oscillation frequency, do we see a 1 over f squared dependence on noise? No, we see 1 over f cubed. But Leison was doing this with phosphor-based oscilloscopes and all kinds of things like that. So he's forgiven for not finding all of these things initially in 1966. So this 1 over f cubed contribution comes from flicker noise up conversion from the device. Okay. All right, so to correct the model, we just make our transfer function y of x of j omega squared equal to f times 1 plus 1 over 4q squared times omega naught over delta omega squared times 1 quantity 1 plus omega 1 over f cubed over delta omega. All right, so this is the modified Leison's equation. This is what we saw for a long time. This f is a fitting parameter or maybe a fudge factor, depending upon like. This has to do with a lot of things. So when you measure oscillators, you use different devices and you have different topologies. So Colpitts oscillators, Hartley oscillators, ring oscillators, relaxation oscillators, they will all have a different fitting parameter. And even if I change devices from a MOSFET to a BJT, that parameter will change as well. This one represents the thermal noise floor. So we have a constant value, so at some point we're going to hit that constant value and the noise is going to stay constant. And then this is the 1 over f cubed portion. And this term, 1 over omega 1 over f cubed, is called the flicker noise corner. And this is dependent upon both the topology and the device that we use as well. All right, so what does phase noise look like in reality? If we measure this with an instrument, and our lab in Mix had a very nice one of these a few weeks ago that we got to test out. You'll see that there's a shape where you get a minus 30 dB per decade roll off of the phase noise. You hit the flicker noise corner, delta omega 1 over f cubed. Then the phase noise rolls off at minus 20 dBs per decade. And then at omega naught, approximately omega naught divided by 2q, you hit the thermal noise floor and the noise stays constant at 10 log of f. All right, so why do we care about Q? Ultimately, basically what we're showing here is that the LC tank is going to filter the noise. That's the higher the quality factor we can get, the better noise filtering we get. Okay. Now, I'll post papers on this, but there are a couple of papers, one by Ali Hajimiri, which is called A General Theory on Noise and Oscillators. What he does is he proposes a method to be able to find basically the fitting parameters using what he calls the impulse sensitivity function. So he proposes a method where we can more accurately predict based upon a topology and a device that we're using what the phase noise will actually be. His method, though, like Leeson's, so Leeson's model actually says what is the power as we go towards DC in Leeson's model. Yeah, it's blowing up towards infinity. So he can't predict what actually happens very close to omega naught. There's another guy who was working at Bell Labs named Alper Demir, who has a more complete theory that actually does predict very accurately what happens to the phase